Let us start this lecture 6 with a statement given by Professor Albert F. Jam in 1912, who was the first person to establish an aeronautical lab in USA. He states, theoretical fluid dynamics being a difficult subject is for convenience commonly divided into two branches. One treating of frictionless perfect fluid, other treating of viscous or imperfect fluids. The frictionless fluid has no existence in nature, but it is hypothesized by mathematicians in order to facilitate the investigation of important laws and principles that may be approximately true of viscous or natural fluid. If you consider this statement that the fluid is basically viscous in nature, whether you like or dislike it. Why it is so? Why nature is so what you call kind to us to be or unkind to us to be viscous in fluid? Is it good or bad? Always aerospace engineer will strive to reduce the viscosity. We have seen in the last lecture that whenever the viscosity flow is viscous in nature, naturally what will happen? The drag due to viscous effect will be higher, right. That is another kind of drag as well. What is that drag? That is due to the pressure or the form, right. So, body has to be streamlined to have a reduction in form drag. However, you are having a increase in viscous drag because surface area increases, right. But we always try to reduce it. Why it is so? Can anybody tell me? The viscosity is a problem, but it can also be a solution to some extent. Otherwise, if viscosity is not there, right, can I really make it to fly an aircraft? With this question, we will move into several other aspects what we discuss. Just to recall that we discuss about the effect of viscosity on the fluid. There are three effects. One is your what you call the drag, right. Other is the effect of this boundary layer, and other is what you call it as a aerodynamic heating, right. These are the three effects what we talked about. Then subsequently we discuss about steady and unsteady flow. Now, I am having one question to you. Do you really understand what do you mean by steady and unsteady flow? I will ask this, we will try to answer this question today, and I will check whether you have understood really what do you mean by steady and unsteady. But before getting into that aspect, let us look at how many ways we can analyze the flow. We can think of the flow to be one dimensional flow, two dimensional flow and three dimensional flow, right. If you look at all the natural flow will be three dimensional in nature. What is the meaning? All three dimensions. When you talk about dimension in a space, if I go where I will talk about dimension, right. When I take this room, I will be having certain dimensions, like I can say along one from a corner of a room, I will say that it is one is x direction, other is y direction, other is vertical, one is your z direction or vertical direction, right. But in the space what we will talk about it. So, that means the fluid if you look at is basically three dimensional in nature, but however for our own simplicity or to analyze it, we always talk about a one dimensional. What is that? One dimensional flow is one in which the flow field will be not remaining constant in other two dimension, only it will be varying in one direction, right. In other words, how we will characterize whether it is a one dimensional flow or two dimensional flow? We need to look at the velocity distribution generally, but you can talk about others. So, as temperature distribution and what you call the other properties like mass fraction, mole fractions in case of reacting flows, right. So, a flow is said to be one dimensional, two dimensional or three dimensional if the fluid velocities varies in either in one or two or three dimensions respectively, right. Then only we will be talking about it. And in case of a one dimensional flow, which I have shown here, right. If you look at this is a flow over an aerofoil. Where is the flow is one dimensional? Can I say the flow here is one dimensional? Can I say here? Some of you are saying yes. How it is possible? If I say this is my x direction, this is my y direction, right. Can I say flow here is one dimensional? Certainly no, because there is a recirculation, flow is being separated at this point. Similarly, I mean a little away from the leading edge, and in the trailing edge the flow is also recirculated, it is separated and recirculating here. So, I cannot call it as a one dimensional flow. However, to create this kind of images, what you call flow visualization, there are various techniques. We use wind tunnel or a water tunnel, right, which is where you can have a control over the fluid flow velocity and also its distribution. In this case, people have assumed the flow to be one dimensional here. That means, this is the uniform velocity what you can see, right. Is it you can observe this? What are these lines? If you look at these are some lines. What are these lines? These are streamlines. Are you sure it is streamline? What do you mean by streamline? Can anybody tell me, please? What do you mean by streamline?
It is generally the path traced by the fluid particles.
Path traced by the fluid particles in a flow is known as streamline. Are you sure what you are saying?
Velocity is perpendicular at every point on the streamline.
Streamline, that means both are same what you are saying. Am I right or wrong? Can anybody tell me what is the difference between these two, or both are same? In this photograph, is it streamline or path line? Because first definition what it told, it is a path line. Okay. The second definition what it says, it is a streamline. In this case, what kind of lines we are having, because these lines are very important for visualizing the flow, right. So, coming back to this, path line is basically path traced by a fluid element, right. What do you mean by this? Suppose I will take a fluid element here, right, and at time t is equal to 0, let us say it is moves like this, right. That means, at fluid is here and at certain time it will be going over there and other things, right. That means, the time traced by this fluid element along this path will tell me the path line, right. It is here, it will go over there, it will go over there, it will go over there, right. That is known as path line, right. But then when we will call it as a streamline? That means, it is when it is fluid, fluid is having a velocity, right. Yes or no? That means, this is the vector, as you told that streamline will be basically a curve whose tangent at any point is velocity vector at that point, right. Will you call it as a streamline then? right, because I am showing the same thing like in the same line. Can I call it as
For uniform flow, streamlines and path lines are same.
uniform flow?
For steady flow.
I think the second answer what is given by him is the right, is a steady flow. That means what is the meaning? How I will get a path line whenever I am conducting experiment? How? That means that will be time exposure of a photograph or time exposure photograph of a fluid element, right. That means if I take a photograph and look at how this path is traced by a fluid element and for a certain time, then I call it as a what? Path element. But however, if I take a what you call instantaneous photo, right, and then try to look at each point what is the velocity vector. For example, let us say this is the my flow is taking place there. I can say that this velocity is here and this velocity here, maybe this velocity is there at that point, right. Right. That means this picture I have taken at one frame of time, maybe at instant, right. And what I need to do? The fluid element will be there and then it is some I am just taking a vector looking at velocity. Velocity is a vector quantity, it is having magnitude, it is having a direction. So, then I call it as and I can obtain if I will be getting what you call a single frame of a motion picture of the flow, right. So, I can take a video at one instant of time, right. I will get full what you call view of the entire domain on which I have focused, right. That is basically a streamline. But when I take this time t is equal to let us say 1 second, this image this path may take a different path kind of things. This can take a different path, right. So, then this will be what you call unsteady phenomenon, right. That means, I am at the same location, same. If I take this is x and this is y, I am having certain distance here, the distance is almost same, but I am plotting at different time step, right. Okay. Upon this reference O, it is having same dimension, let us say 3 meter from one side, another point is 4 meter, x is equal to 3 meter, y is equal to 4 meter. At this point, I am measuring a point. So, therefore, I am keeping my probe or looking at it at the same point, but I am measuring. But if this path is same as that of the at time t equal to 1 second, at time is equal to 0 is same, then both the path line and the streamline will be same, right. Generally, that means under steady state condition, streamline or path lines are same. So, we generally try to conduct experiment like this to what you call such that we will have a steady flow and streamline path line can be same. These are very important concept. If some of you may not have what I have seen, you are getting confused. So, it is very important to know about it. Here I can say the flow is one dimensional in nature, and let us look at two dimensional in nature. This is a duct, right. It can be a circular duct, it can be a square duct, but we always like to have a circular duct kind of things, right. And it can be a channel as well. If it is a channel, what it will be? It will be two dimensional flow. You understand what do you mean by channel? If I draw here, I am just drawing in this figure, right. Flow is coming over here. Will you call it as a two dimensional or channel flow, or can I call it as a what you call a pipe flow? Can I call this from this drawing? I am talking about, I am asking very simple question of drawing. From this drawing, can I say whether it is a channel flow? Channel means what? That means along with this direction, the flow is, remains what you call uniform, should be or need not to be, what it should be. That depends on what is the inlet condition. If we are having uniform flow at the inlet, it will be not changing because dimensions are quite big. There is no boundary layer effect, both this side and then this side, kind of thing, right. But is it a pipe flow or not? What kind of dimension I will be talking about, right? Will you call it as a 2-dimensional flow or a 1-dimensional flow, right? What I have shown here in what you call a velocity profile here at A, and there is another velocity profile at B. Will you call it as a 1-dimensional flow or 2-dimensional flow? In this case, if I take my x direction here, and if I take this is my y direction, right, and if you look at my velocity profile is changing along with the y direction, because here this is a higher velocity, this is a smaller velocity, and if I am moving toward this, my velocity is changing. That means, if I am at A location, I am B location, then my velocity profile here it is different. At the center line, this is higher, this became a smaller. So, therefore, I am having 2-dimensional flow. Am I right or wrong? All agreeing. But if I am considering only in one domain, then what will happen? I will consider only in this region, what will happen? Or I will consider in this region, what will happen? In this region, in the entrance region, where there is no divergence, it is just not changing, diameter remaining same of the pipe or the channel, I am talking about channel, and then there is a change in the channel, right. And if I am looking in this domain, what will be flow? Will it be 1-dimensional or 2-dimensional? See, this is very important to appreciate or recognize whether the flow is 1-dimensional or 2-dimensional, right. Because the analysis what we will be carrying out considering in propulsive devices, mostly either it is a quasi 1-dimensional or 2-dimensional, right. We need to understand what do we mean by quasi 1-dimensional and 2-dimensional, and how we will handle that little later on, but you might be aware, but you think about what it would be. So, this is what I told, it is a channel kind of things, because this dimension is not telling me, because if it is a pipe flow, what it could have? If it is a pipe flow, I could have a line here, isn't it? Or I could have taken a cross section which is looking at, then only I can say it is a pipe flow, right. So, let us look at flow through a pipe. So, if you look at this is a flow through a pipe, I have shown here. You look at here at the entrance, it is having what you call a uniform velocity profile, and keep in mind that this is your what you call z direction, right, and this is your, or I can say this is your z direction, this is your r direction, right, and this is a what you call another coordinate system, what we will talk about it, that is known as r theta z coordinate or the cylindrical coordinates, right. In this case, what we are considering in the z direction, keep in mind that in this figure z direction in this is a from left hand side to the right hand side, and this is a r direction, right, and theta direction is here, it is moving. So, you take a this thing and move around a theta, then you will get a pipe kind of things, right. So, here we are considering basically a z and r, right. That means, velocity is changing along the z direction. If you look at started with uniform velocity, what happens to this velocity profile? It is different than the beginning of the uniform velocity profile. It goes on changing, right, along the z direction, yes or no, right. And also it is changing particularly here along the radial direction, yes or no, right. In this point it is all changing along with this, whereas at the entrance there is no change in velocity along the radial direction, but what happens to theta? Is it changing or not? In this figure what I have drawn, or we can assume here that it is only the velocity particularly is changing along with the r and z direction. That means, it is a two dimensional flow. Can I call it two dimensional flow, or I will have to say two dimensional axisymmetric flow, or in simpler axisymmetric flow kind of thing, because along the theta direction I am saying it is symmetric. So, I need not to consider it is uniform, that, right. So, you need to understand what is the difference between pure two dimensional flow and axisymmetric flow. It is very important, because we will be dealing with axisymmetric flow most of the times, right, because all our aerospace ducts and other thing will be cylindrical in nature. So, cylindrical coordinate system is more natural to be used, right. And what happens to the velocity you look at here, like it becomes changing, and when you go to here there is an increase in this, and then it becomes also becoming changing, and what is happening here? The velocity profile is almost similar to that, right. And in this, what is happening? If I compare these two velocity profile here and here, what is happening? Can anybody tell me? One D flow. How you are saying it? It is not changing along with the z direction. However, the change in the r direction, right? This is r direction, it is changing, right. So, therefore, we can call it as a one dimensional flow, but why it is happening? Why? Means why it is fully developed, you call? How it is happening? It is because this line what I have shown here indicates the boundary layer which is grown from the inlet of the pipe, right, and it merges. After that, there is nothing really happening with the boundary layer, because boundary layer, two boundary layer, upper boundary layer, lower boundary layer. Of course, I can't say upper and lower, but it is a pipe, right. If it is a channel, I can say upper and lower boundary layer. In a pipe, what I will say upper and lower? It is along with the theta, like whole circumference is being merged, and when it is merged, that is known as fully developed flow, and for that equations are there, Poisson equations, you can solve that, you might have exposed in your fluid mechanics course. But now, what is happening to this velocity in this zone? What I call these velocities and these velocities and these velocities, what it is, right? This is known as the cohesion, right. Okay. In your jet flow, you must be knowing, we will be discussing little later on jet flow, right, where the cohesion is there. What you call it as a cohesion, I will leave that question. Now, let us get into at what distance I should get a fully developed flow. Will it be dependent on what? Will it be dependent on inlet velocity profile? Will it dependent on the how this flow is entering? Basically, I am saying the same thing in a different word, right. Then what else? Will it be dependent on laminar or turbulent nature of the flow at the inlet? Will it depend on the friction or the roughness of the pipe and the material of the pipe, if I want to determine where I can apply the two dimensional equation and one dimensional equation for analysis. That means, in this region under developed flow, what is known as, or developing flow, you can say, in this region from here to here, this region, it is basically called as a developing flow or underdeveloped flow, whatever you call, right. I think developing flow is a positive word, like we are developing country. Okay. So, there what you need to consider, whether the flow will be two dimensional or one dimensional, it will be two dimensional. That means, you need to consider the governing equations that. So, how we will go about it? It is basically L by D. If I take this diameter of the pipe for a fully developed flow, will be dependent on Reynolds number, right, Reynolds number, right. And for a critical flow, that means, where it will go from laminar to turbulent, L by D for a fully developed flow will be around what? Around 125. This is a rough number or a thumb rule, you can say. And in case of turbulent flow, it will take more length to be fully developed for a particular diameter or not, or less. It will be taking less distance, right. And these are very important for analyzing and developing or designing anything. Okay. So, I will stop over here, and then we will be moving, of course, before getting into that where we are discussing, there is another coordinate system which is being used, is known as spherical coordinate system. This is basically r and phi and theta direction. We will not be using very much, however, you might have exposed to some other, but we will be mostly using, this is known as a cylindrical coordinate system. So, let us get back to our this thing, like a three dimensional flow, right. See, if you look at flow over I have taken a spacecraft here, and you can see these are the lines which indicates it is you can say this as a path line, and if it is a steady flow, as I told, it can be streamlined as well if it is a flow is steady, right. So, these lines are quite three dimensional in nature, therefore, you can call it as a three dimensional flow. So, now we have talked about very what you call qualitatively about the flow, but we need to now deal with the flow quantitatively, because we will be using this for designing certain thing. That means, we need to quantify or look at various properties. For that, we will have to consider the governing equations that will basically dictate how the fluid flow will be there. That means, I can really understand or simulate the fluid flow by using certain governing equations. So, for that we will make some assumptions. I have already talked about it. What is the continuum flow? That means, we will be considering continuum flow in our analysis all the time, except of course, whenever you go to the space at a very what you call low pressure, there the various kinds of flow will be coming into picture, as I told, sleep, no sleep flow, and then free molecular flow kind of things, but we are not bothered about that. And as I told, we will be considering basically about the Newtonian fluid, right. So, we will restrict our discussion to a single phase fluid, and as we are dealing with the mostly the gases, right, then we will be considering as a perfect gas. What do you mean by perfect gas?
No reaction takes place.
No reaction takes place, we call it as a perfect gas. Can anybody tell me, please, what do you mean by a perfect gas? Or
intermolecular forces are considered negligible.
Intermolecular forces between or among them in a gas will be very, very small, right. When it will occur? When it will occur, these intermolecular forces will be less. it can occur only when the pressure will be low. What kind of low, which can tell us that whether the flow is or the fluid is perfect or not, or gas is the perfect or not. Is it the only condition, or there is some another condition which will tell you whether the gas is perfect or not. The volume occupied by individual particles or the molecules will be quite less as compared to the volume of the fluid which you will be considering, right. Then only if both these conditions satisfied, then only one can call it as a perfect gas, right. And where ideal gas law P v is equal to nRT will be applicable, right. Yes, yes, it will be, but then that connotation will be little different. Perfect liquid will be there when you call about kind of things, right. Okay. So, here when you are saying perfect, actually this perfect is not a good word as such, right, because we are saying it is be satisfying a very simplified form of equation state, what is known as ideal gas law, right. Then we are calling it as a perfect gas. Actually, I will say that is rather this is an imperfect gas according to my version, okay. But people are saying we will have to go by that word, okay, naturally. But the question is that like what we will call at what pressure, what temperature we can talk about whether the flow is perfect or not, or whether it will follow the ideal gas or not, law or not. Is it, if I take ambient pressure in the air in this room, let us say at ambient temperature, can you call it as a perfect gas and then apply the ideal gas law? Yes or no? But I want answer, all those things, this you are learning from your class, I think maybe 10th onwards. Ideal gas law is being taught, I think, right, and you are being engineering already. So, you know all these things, right. Then how I will talk about it? Then you will have to go and look at it, compressibility factor, right. And let me tell you that you can really consider the gas to be an ideal gas, right, even at a pressure, atmospheric pressure. Not only that, even at a very high pressure, even up to the 100 atmospheric pressure at ambient temperature, you can consider it. And if you increase the temperature, naturally you go for even consider an ideal gas law, you can apply the ideal gas law even at higher pressure, because at the at a higher temperature, at the higher temperature, even at higher pressure, molecules will be far away, right. So, therefore, you can consider, and some of you who are not having any idea, I would urge you people to look at in thermodynamics book about compressibility effect, and we will be dealing with compressibility, compressible flow from a little different perspective as well. So, and we will be ignoring the body forces, right, and what will be the unknown in case of generally I am talking about, of course, we will be more interested in density whenever we talk about compressible flow, and velocity, pressure. When you talk about velocity, as I told, if I am considering 3-dimensional flow, naturally it will be flow along with the x, that is V x, V y and V z, but mostly we will be dealing with, as I told, quasi 1-dimensional flow or 2-dimensional flow at the most, because it will be difficult to solve the equation in 3-dimensional nature, and pressure and temperature kind of things. And for deriving this governing equation, we will be what we call applying the conservation of mass, what we call it as a continuity equation. I call it as a law of common sense, right. That is, what it states that whatever the mass accumulated or depleted is equal to mass in minus mass out, and I always consider mass can be compared with the money. Money is coming in and coming out, and whatever it is accumulation or it will be reducing or depleted. So, conservation of momentum, which we have already talked about it, and whenever it will be applied, what to call this thing, basically we have just initiated discussion by invoking the second law of motion, right, Newton's second law of motion, and when it applied to the fluid flow, it is known as Navier-Stokes equation. You will see maybe today itself that it is quite complex in nature, right, and it is quite difficult to solve these equations as well. So, conservation of energy, which we have already discussed about it by invoking the first law of thermodynamics, both for the control mass system and control volume systems, particularly for control volume we will be using, and this is known as energy equation. I have told you equation of state, and we will be using ideal gas. There are several equation of states. Okay, we will be using ideal gas law. So, these is the basis for deriving the governing equation, and all fluid dynamics is contained in these conservation principle along with the equation of state. Whether it is a Newtonian fluid, non-Newtonian fluid, of course, the constitutive equation will be what to call different, but however, it will be similar so far this principle is concerned. And keep in mind that I have told you that we will be talking about single phase flow, but in our aerospace application we need to look at also two phase flow, where the two phase flow will be coming into pictures, particularly when we are working with the liquid fuels and solid fuels, like in rocket engines or a gas turbine in liquid fuel. So, also in the rocket engine we will be using the liquid fuel as well, but rest of the things will be, but how we will handle? We will not handle those things in a traditional way of two phase flow, but in single phase flow. As you go along, we will be discussing how to handle from the engineering perspective without complexing or without really involving complex mathematics, which is untractable. So, we need to look at this, how to derive this equation, which will be helpful, right. There are two approach in that. One is what you call the integral approach form, other is your differential form. That means, I will take a small elements and then look at it, this balances mass or the momentum or the energy, and then look at it where this delta x or the scale will be tending to a 0, then I will get a differential equation. But however, when I take a bigger volumes, control volumes, and look at as if the flow is taking place throughout and looking at that inlet and outlet, then we consider as a integral form. For example, if I take a arbitrary control surface here, a control volume having a control surface, and if I take the streamlines I have shown, right, which is entering through and going out some inlet and outlet, and if I consider a small surface area here as an element which is having d A, and of course, it is having a volume d V, and it is having a vector V, and you keep in mind this is a unit vectors that gives you that is perpendicular to the to this surface. Always this unit vector is perpendicular at that point where you are considering, and the angle is theta between the velocity and the normal or the unit vector. So, and then what we need to do? We need to use basically theorem, which is very important, particularly when I am talking about from differential to the integral form, that is known as Reynolds transport theorem. We state that rate of growth of n matter that means is a continuum flow. So, there will be a lot of matter will be there and we call it as a n matter, and what is that n, I will talk about it. That is basically total value of a property over a control volume, what you call rho, psi and dV, and where dV is basically the volume element of this small what I have taken. Now, that rate of growth of n matter is basically rate of accumulation in CV plus actually there will be equal sign here, right, is equal to net flux minus the okay, that is a net flux minus net. That means dN by dt will be is the rate of accumulation of in the n in the control volume. If I say dou by dou t psi rho dV plus this is the term which is basically net flux in flux minus net flux, that means this is equal to that. So, therefore, that will give you the Reynolds transport theorem, and keep in mind that for whenever you are talking about continuity equation, this psi will be equal to 1, whereas for the momentum and other things we will have to consider v basically velocity, and then for other thing it will be energy, the psi can be any property as a matter of fact. So, in addition to this, like we need to concern about various other equations or constitutive equations for relationships such as stress strain relationship, temperature heat flux relationships, or a diffusion relationships and other things. So, keep in mind that this Reynolds transport theorem is very important, particularly when you talk about this converting this into differential form to integral form and the vice versa. So, let us look at the basic governing equation for fluid flow. We will take this control volume as I have shown here, and for the continuity, if you look at a differential form, that will be dm by dt, that means the amount of mass changing in the control volume with respect to time is equal to mass is entering into the control volume and mass is going out of the control volume. So, if I consider this is a basically differential form, and if I consider this as my element, and then we will have to look at how this elemental mass flow rate would be basically dm into, I will have to consider rho and velocity, and if I look at this vector, that means along with this will be cos theta and dA is area, that means mass is entering, mass is going through this area, and if I mass within this total control volume, because in control volume I am taking this element, now I am considering the total control volume, it will be basically m dot rho dV, right, because this will be a volume, right, and where dV is the volume elements, and by using above expression, integral form of continuation can be derived as that d by d rho dV plus rho v dot n dA is equal to 0, right, and this is the continuity equation, and from the integral form, and this is the differential form, above equation expression can be obtained directly from the differential equation using the Reynolds transport theorem. And we will be looking at momentum equation, right. According to the second law of motion, we can have F is equal to k into d by dt mb. This is your second law of motion. That means, change in momentum with respect to time is nothing but your force force is proportional to change in momentum time, and k is your proportionality constant, and in case of SI unit k is equal to 1. Now, we will have to apply this what to call the second law of motion for a fluid flow. So, when we will do that, what we will do? We will have to basically look at take that control volume what I have taken, and we can see that will be this is your what you call convection terms, and this is your unsteady terms, and which is nothing but the summation of force which is acting on the fluid element. And what are these forces? These forces will be having two kind of things. One is your what you call pressure, due to the because the fluid will be moving due to the pressure gradient. That means, that will be acting like a normal stress. If you look at here, in this case is a fluid element, and this delta or sigma x, which is corresponding to the pressure which will be acting, and this is portion is basically the shear which will be acting like, for example, tau x y, and in this case the plane in this case is basically, if you look at, this is your what you call in x, this is your z and y plane, and this is in the what you call x and y, that means is acting in this direction. So, then similarly other places it will be having several of shear stress which will be acting. So, if you look at it, is basically a tension, right, which you can see from this figure, and this has to be integrated over the area. And there is also a body force which we consider generally gravity, for the completeness sake I have taken here, and this is with respect to volume. Keep in mind, this is the force is basically with the area surfaces is being acting. So, therefore, this is known as surface forces, that means is having normal and shear, and there will be a body force which will be due to gravity and other effects like electromagnetics and other things. So, if you look at, this is basically the equation of the what we call the momentum equation, and similarly energy equation you can write, which we have already derived, and then we will be looking at unsteady part, and this is your what you call total energy, and this is the heat being transferred or the heat interaction between system and a volume. There is a shaft work, and there is also a what you call body force, due to that some work will be there. So, for an ideal equation, as I told you, P is equal to rho R T, and where R is equal to R U divided by molecular weight. This is the universal gas constant, the molecular weight, and what we have seen, these are the equation we need to consider. But what Richard Feynman has told, you may derive equation, that is not good enough. What is he says that we have written an equation does not remove from the flow of fluid its charm or a mystery or its surprises. With this I will stop over, and I must tell you that these equations you can derive of your own, and having derived, that does not mean we are having solutions for that. So, with this we will have to stop over, and we will discuss in the next lecture.